Hi, everybody. It's Miss Weeson, and this is the sixth and final podcast in our Unit 3 on intermolecular forces. And what we're going to do here is just finish up this unit by talking about a variety of lab techniques and lab skills that actually relate to intermolecular forces. And so, what I want you to do as we go throughout and I explain some of these techniques, I want you to think about in the back of your mind, how do these lab techniques relate to intermolecular forces? Now, truth be told, if you take a look at the first skill and technique, which we call chromatography, okay, we're actually going to do a lab next week on chromatography. So, what I'm just going to do here is very briefly talk to you guys about the concepts related to chromatography. So, ultimately, what is chromatography? Chromatography is a laboratory technique that we're going to use to separate mixtures. And ultimately, the way that this happens is through the different strengths of intermolecular forces within that mixture. And so instead of reading verbatim what the notes say, I want to draw your attention to this image down here. And I want you to see that chromatography is going to happen in several steps. Now, you need to understand in class, we're going to do paper chromatography. It is the simplest and cheapest way to do chromatography. However, when you get into more advanced labs that are well funded and have more very particular assays and research, you're going to start getting into things like thin layer chromatography or column chromatography. There are multiple types of chromatography that are applied in various settings, okay? And so the easiest way to understand this is by looking at the images that I have put into your notes. If you take a look at step one, you're going to see that some type of, for lack of a better word, plate. This plate could be a silica-based plate, or in class, you're going to find that this will be actually a filter paper. We call it actually chromatography paper. Anyway, the plate or the filter paper is going to act as the stationary phase of chromatography. It's not going to move. It's going to sit there in some type of chromatography chamber. And so if you take a look at this image here, this chromatography plate has been placed inside a beaker. So for lack of a better word, we can call this environment the chromatography chamber, if you will. So we're going to have some type of stationary phase, and then we're going to add to that stationary phase a sample or a mixture that we are curious and separating and learning more about. So you can see on the picture that the sample spot in purple has been indicated to you. It's been dotted at the bottom part of this plate or filter paper. And what we're going to do is we're going to add that filter paper and plate into a solvent. Now, the solvent is called the mobile phase, okay? And the reason why we call this the mobile phase is because once we place the chromatogram that contains our spot, our mixture that we're curious about learning more about, once that chromatogram paper comes into contact with the solvent or mobile phase, the solvent is actually going to travel upward and work against gravity through something called capillary action. We also call that wicking action as well. And so what you can see here in step two, now we are on the second image, the solvent starts to travel up the chromatogram. And what you should notice is that that dye or that spot is going to separate out into its different components. And it's going to do so based on polarity. And so as the solvent continues to travel up the chromatogram, the molecules that move further up the chromatogram are going to actually have a greater affinity for the solvent itself. So they're going to have a greater affinity for the mobile phase. Whereas molecules that stay further down on the chromatogram are said to have a greater affinity to the actual paper itself. Again, there's going to be a lot of applications in chromatography across industry and within our lives. You're going to do a lab next week and take a deeper dive into that. So we're going to move on for now. The next application or technique that you need to be familiar with, and it's unfortunate that we're not going to be able to do this lab, but you will be doing kind of an activity to kind of help you tease out the concepts of what distillation really is. So distillation, you probably have heard this before. We use distillation on many, many aspects in our life. We use this in the petroleum industry to separate petroleum out into its various products. We use distillation in the production of alcohols, in the production of essential oils and things like this. So distillation is a huge laboratory technique used and performed on many different scales. You can see by the image that's been provided here, the setup looks pretty much like an episode coming out of Breaking Bad. Lots of glassware. But ultimately, what you're going to do is you are going to distill a sample. I'm going to highlight it here in your image. If you look at that flask, we will make the assumption that there are multiple substances within that flask. So a mixture of liquids. And ultimately, what distilling is going to do is it's going to take advantage of boiling points of different substances, and it's going to essentially separate those liquids out based off of their boiling points. You will take some type of heat source here, like a Bunsen burner. You will apply heat to a mixture of liquids. As a particular temperature is reached, the substance with the lowest boiling point will actually have their liquid state convert to their gaseous state. And so the vapor pressure or the gaseous molecules of that substance are kind of captured at the top part of the interface of this flask. As the thermometer indicates a temperature rise, what's going to happen is these vapors, these gas molecules, are going to rise up into something called a condenser tube. That condenser tube, which is going to be surrounded by cool water, cooler temperatured water. The gas molecules will travel in the middle of this condenser tube. And as those gas molecules come into contact with the cold environment around it, so the cold water, those gas molecules are going to now condense back down into their liquid state. And so what you would have here is that if we have a certain temperature that's being reached, and that liquid is boiling off, then you're under the assumption that whatever is being captured on the right side into this flask is actually a pure substance. Okay, so again, you are going to do an activity, not so much a lab on this. I hope to write a grant in the future to get a bunch of glassware that way we can actually do a distillation lab. Okay, you're also going to do and learn a little bit about something called spectrophotometry. Now, there are many different types of spectrophotometry that are used and applied in our world. And basically, this is a method on how to measure how much of a chemical substance absorbs light by measuring the intensity of the light beam as it passes through a sample. And you can kind of see here that image to the bottom right here kind of illustrates that. You're going to have a light source. It's going to enter into a slit. It's going to probably be beamed in some type of prism to refract or separate a light into its different wavelengths, at which point any light at a particular wavelength will be allowed to pass and transmit through a substance that we are calling the sample in this picture. And so basically the principle behind this, you guys, is that compounds are going to absorb or transmit light over certain ranges of wavelengths. And so one thing that you're going to need to prepare yourself for and get comfortable hearing is something called the Beer-Lambert law, okay? And this is basically where we can measure the amount of a known chemical, so we know a substance with a known concentration, and we can actually use the Beer-Lambert law to determine the concentration of a substance that we do not know the concentration of. You can see that this device here, you open a compartment, you insert the sample into this device, you set the device up to bombard that sample with a particular wavelength, okay? And so what this spectrophotometer is going to do is it's going to bombard the sample with light, and that sample will either absorb or emit photons. Remember, we've heard this word before. Photons are simply just packets of energy. And so the molecules that are within these samples are going to start vibrating. Even solids have vibration. Now, it's not going to be as much as a liquid. And certainly, liquids aren't going to have as much vibration as substances in their gaseous state. But you must understand right now that all molecules within samples are going to have vibrations. Okay. And so what's going to happen is when you bombard samples with different types of energy, they're going to have these things called transitional states. And so, depending on the type of wavelength that you're bombarding at the sample, it's going to have a different vibration based off of the type of radiation you're using to bombard that sample. If you bombard a sample with microwave radiation, and again, you can look at a spectrum. So just bear with me here. I'm going to scroll down. On the next page, you're going to see the spectrum of electromagnetic frequencies that we have here on Earth and in the universe, at least as far as we know. And you can see that the microwave radiation falls right here, not quite right in the middle of the spectrum. You guys all should be familiar with what microwave radiation is. You guys probably have at some point in your life used a microwave to cook your food. And when you do so, that type of radiation is going to cause transitions in what we call molecular rotational levels. Now, don't let the language get you caught up here. Molecular rotational levels literally just help a scientist understand the bond angles that make up that matter. So bond angles, remember you guys, we learned the VSEPR model and how we can actually predict molecular geometry, look at lone pairs, determine where these bonding elements are within a molecule and the bond angles that they form. Why is this important? Well, the molecular geometry and therefore bond angles will give us insight on how those substances will react with other substances. Okay, let's take a look. And if we bombard a sample with infrared radiation, okay, that is going to help scientists understand transitions in molecular vibrational levels. Okay, that is just fancy words for helping scientists understand the bond type and the structure of the matter. So we've learned about bond types. You guys, these are not intermolecular forces. When I say bond type, rather, I'm talking about ionic bonds or covalent bonds of polar and nonpolar and metallic bonds. Okay, so infrared radiation allows a scientist to take some substance that we don't know about. We bombard it with IR. It creates vibrational changes within that substance that are then measured. And those measurements tell a scientist about the types of bonds within that substance. You guys, why is that important? Well, what lab did we do in Unit 2? We had a whole bunch of unknown chemicals that had labels falling off of them. And because of safety reasons, we need to know the types of bonds that these substances have so we can classify them better. But also, knowing them in other industries like the medical field would be really important, right? Lastly, the type of radiation that causes some transitions within matter is ultraviolet and visible radiation. Now, again, let's go down and scroll really quick. I neglected to show you where IR was. So here is infrared radiation. And then the one we're talking about right now is visible light and UV. So you can see within this band on the EM spectrum that if we bombard substances with these types of radiation, it allows us to understand the structures of matter based off of the vibrational and rotational transitions that the substance occurs. So lastly, ultraviolet radiation or visible radiation, when bombarded at matter, can cause transitions within the electronic energy levels of a substance. Well, what does that mean? That's just fancy way of letting scientists understand more about the electronic structures of matter. So the electron configurations, how many electrons there are, how big an atom is, etc. So you can see here that microwave, infrared, UV, and visible radiations can cause different transitions within matter. Those transitions give rise to different types of molecular movements. They could either be, one more time, you guys, rotational, vibrational, or electronic. And what that translates to is either a description or an understanding of the bond angles, the bond types, or the electron or electronic structure of matter. Practice problems, I just wanted to mention the Beer-Lambert law again. You are going to see that this equation, the Beer-Lambert law equation, is actually given to you on your AP reference sheet. So what I want you to do right now is pause me, pull out your AP reference sheet, find this equation, and if you need to and want to, I would suggest that you label it on your personal AP reference sheet handout. Capital A, which is representing absorptivity, so the absorption of light, if you will, is equal to epsilon. This is a constant, you guys. It's a molar absorptivity constant that, depending on the substance you're using or looking at, would have a very specific molar absorptivity value. You're going to see that lowercase b is the path length that the light is traveling within the spectrophotometer, and that lowercase c is the concentration of the solution. You will be expected to use this equation and apply it. Now, I want you to know I am going to have you guys do a virtual lab, likely to kind of highlight using this equation a little bit more and getting more comfortable with the Beer-Lambert equation. Ultimately, at the end of the day, you're going to use this equation to determine the unknown concentrations of solutions. All right, and again, this is not the first time you have seen the electromagnetic spectrum. Here on Earth, we are really only privy and can visibly see the visible light spectrum, although we are aware of the other types of radiations. Again, look at the spectrum here. It should all look very relatively familiar. We are talking about frequency and wavelength here, you guys. And so for us to better understand, Beer's law and spectrophotometry, and to better understand the electromagnetic spectrum and how all of this is interplayed, we need to, again, take a look at the speed of light equation given to you on your AP reference sheet and Planck's equation as well. Let's go ahead and apply some of these concepts, these lab techniques that we've just learned about, into some other areas that you might see and other questions that might be asked of you on the AP tests, or what things that we might be doing in class. Okay, let's talk about something called the photoelectric effect, and this is in exercise 30. The photoelectric effect, we learned about this briefly when we studied the photoelectron spectroscopy. That's basically when we took a light source, a source of some sort, rather, that emits some type of energy, some type of electromagnetic radiation, if you will. And what happens is you then bombard a sample, an unknown sample, with that photon source. When that energy source hits that sample, it excites the electrons to come flying off the sample, which is what you're seeing over here. Now, those electrons can be captured by some device and measured. We can understand a little bit more about the energy it took to eject those electrons. Okay, so let's take a look at what this question's asking. It says the diagram represents the photoelectric effect for a metal. When the metal surface is exposed to light with increasing frequency and energy photons. And remember, you guys, when we are increasing frequency, let's go ahead and take a look back up here. If we are increasing frequency, we are going this way on the EM spectrum. So as a quick reminder, our gamma rays right now on the known spectrum have the highest frequency. Okay, so anyway, this metal sample is being bombarded by some type of radiation source with increasing frequency. Okay, and the electrons that are first to be ejected from the metal have an energy of 3.3 10 to the minus 9. So now the question is then asking, basically, which of the following is the closest frequency? And remember, you guys, frequency is that V-looking structure. It's not a V, though. So what is the frequency of light when the photon has an energy of 3.3 times 10 to the minus 19? And you guys, J is joules. So really quick, I just write my givens, and I know that they gave me E, energy. and that is 3.3 times 10 to the minus 19 joules. One of the things that I realize is that if I go back and look at Planck's equation, I've been given energy. I know that H is actually a constant we call Planck's constant, and it's asking me to solve for frequency. So it looks like I can actually use just Planck's equation here, rearrange the equation to solve for frequency, and then I will have my answer. So really quick, let me go ahead and write also on my givens down here. I know Planck's constant. I'm pulling that right off of my reference sheet. I don't need to memorize it, joules times second. And I'm going to use E H mu. Okay, I'm going to rearrange the equation. Frequency equals energy divided by Planck's constant. And I like to say at this point, plug in your values and just calculate. So plug and chug. Okay, so what units cancel? Looks like we're going to have joules that cancel. And that's great because frequency should be in s to the minus 1 or 1 over s. So when I do my calculation here, plug this on my calculator, I get 4.980 times 10 to the 14 s minus. Now, if we really wanted to fall in pecking order, we would look at 2 sig figs. 3.3 times 10 to the minus 19 is only 2 sig figs. So we should actually just report this to 2 sig figs, which I would then do rounding. 5.0 times 10 to the 14 s minus 1. Okay, so there's a little application there. So in exercise 31 rather, it looks like we're doing a little bit more on the photoelectric effect. It's saying, hey, the diagram above, and it looks like they're still referring to the diagram in the previous exercise problem. But it's saying, hey, that metal is being exposed to a light that has increasing frequency, and therefore the energy of the photons increases as well. And so the electrons that are first being ejected from this metal sample has an energy of 3.3 times 10 to the minus 19 joules, just like the last problem, you guys. But this time it is asking us, using wavelength information, can you tell us, using wavelength information, there's the wavelength simple lambda, what is the color of light that is going to actually be emitted here? So we have our givens, and I will go ahead over here on the left-hand side and just write what has been given to me. Again, I know E, 3.3 times 10 to the minus 19 joules. Okay. Now, if we are asked to determine the wavelength of light here, we need to understand that we're going to do this in 2 steps. The first equation, we're going to use Planck's equation. Energy equals Planck's constant times frequency. Okay. And really quickly, you'll notice that frequency was not given to you in this particular problem in exercise 31. However, we were given energy, and we know H because H is a constant. It's Planck's constant, remember? And that is 6.626 times 10 to the minus 34. Let me go ahead and cram my units in here, joules times second. So the first thing I'm going to do is rearrange this equation just like I did in the last problem to solve for frequency. And so frequency is going to be energy divided by Planck's constant. And let's go ahead and plug and chug those values really quick. I put these in on my calculator, and I got the same answer as last time. And so now I have frequency, you guys. I know the frequency is 4.980 times 10 to the 14 s minus 1. Now take a look at our other equation that we oftentimes will use in junction with this. Let's scroll back up, and that is the speed of light equation. C is the speed of light. It is a constant. It is a known, and it's given to us. You do not need to memorize it. And we are going to need to know 2 things. We're going to need to know the wavelength and the frequency. So if you take a look, C equals lambda times frequency. Well, guess what, you guys? We know the speed of light, that's a constant, and we know the frequency. Now we can simply rearrange this equation to solve for wavelength. And so bring frequency to the other side. By the way, I'm going to continue to build on my list of givens. I know C. I know what the speed of light is. 3.0 times 10 to the 8 meters per second. So again, let's just do some plug and chug. Seconds cancel. I'm left in meters, which is exactly what wavelength can be measured in. Oftentimes it's nanometers, but in this case, that could be an easy conversion if need be. And so I got my answer on my calculator, 6.0 times 10 to the minus 7 meters. And if we converted that to nanometers, it would be about 600 nanometers. And if you take a look, that looks like it falls into the orange range. So it looks like in this particular case, the color of light that would be bombarded on this metal sample would be orange to our eye. Okay, last problem, you guys, and then we are going to end this chapter, and that is talking more about the electromagnetic spectrum and light. It says IR spectroscopy or infrared spectroscopy is a useful tool for scientists who want to investigate the structure of certain molecules. Explain what can occur as the result of a molecule that is absorbing a photon of infrared radiation. Okay, I'm going to go ahead and jot down my answer. This is a response, not a calculation so much. So why don't you pause me, go back up into your notes, and tell me what happens to molecules in terms of their movement when they're bombarded with IR radiation. You put your answer, I'm going to put my answer, you come back and check. Okay, so it's asking us again what infrared light does to matter. Okay, and I said that the energies of IR photons are in the same range as the energies associated with different vibrational states of chemical bonds. In other words, molecules can absorb IR photons of characteristic wavelengths, thus revealing the types and strengths of the bonds that are present in that molecule or that matter, if you will. Okay, you guys, that's going to wrap it up for Unit 3. Thank you so much for watching.